Okay, so we stopped uh, section 2, 0.2 with mapping. So we went through sets. We learned tons about sets. The summary is basically the last topic we covered was symmetric difference and what it means. So to quickly recap on what symmetric difference is. So the formula is basically that represents the formula that represents the union uh, without the intersection. And we've asked the question here on math stack exchange, and we should reference this here as well. So we should have this referenced like that, and that's that. So we stopped with on map on the subject of mapping. I'm not sure what mapping is all about, and I figured maybe we could, yeah, let's. So we covered all these topics, the intervals, and all the good stuff, all the good stuff. So the set notation. So the symbol here means such that x belongs to R, such that x is greater than or equal to 3. And the intervals, and these are basically the set of numbers. You have the natural numbers, the integers, rational numbers, real numbers, which includes everything including floats, imaginary numbers, and complex numbers. Natural numbers 0, 1, 2, 3, 4, 5. So that's that. And then you have the integers, negative, plus, whole numbers. And so floats are not whole numbers. So they are not integers, not fractions. The rational numbers are fractional numbers. And that's that. So yeah. Now, the next topic we will be talking about is, so we've seen that with the notations we could easily define different domains. And as you can see, you have two different terms here. You have the domain and you have the range. The range is something, it's vertical, and the domain is horizontal. So let's go through this. The domain seems an interesting topic to talk about, and set builder notation is very useful for defining domains. In its simplest form, the domain is a set of all the values that go into a function. The function must work for all values we give it, so it is up to us to make sure we get the correct domain. So 1 over x is undefined at x equals 0, and that's dividing by 0. So we must exclude x equals 0 from the domain. The domain 1 over x is all the real numbers except 0. So you can write this as dom 1 over x for x belongs to real numbers such that x does not equal to 0. 0. Okay. The domain of, so the function here is x. So this is the domain. So the function is 1 over x. So the domain of gx equals 1 out of x minus 1. So x should not equal 1, so that we will not get a 0 in the denominator. The square root of x should be also, if it's 0, then we are in a problem. And then the same applies for the other examples as well. So that's the domain. So that's that. That's out of the. So that's the set of all points locus. I think this would be handy to. This is interesting. Alright. So a set is just a collection of things that we know. When we collect all points that share a property, we can add up with a line, a surface, or other interesting things. Now, as you can see, there is a single point with a large interval here. So as the interval grows smaller, the points grow closer to each other until you basically build a line. Now, a circle of points with fixed distance from the center. Just a few points start to look like a circle, but when we collect all the points, we actually have a circle. So you have a circle and a line, and if you draw a line about, you basically, the more you draw, the smaller it is, the smaller the circle, and it could grow bigger. So basically, up on the distance from the, and then you could go all sorts of directions here. And you could also go all different sort of directions here. Alright, imagine this is happening in a 3D space. All the points that are fixed from the distance sphere. So you have all the different, it's not only in one direction, you can go this way, this way. You form a sphere. Locus. The idea of the set of all points that is used so much that it even has a name. It's called locus. Alright, so this is what the locus is, a set of points that share a property. So the definition is, so this is the definition. Let's reset this notes page and then have this notes noted down. So a circle is the locus of points on a plane that are fixed a distance from the center. Note, locus usually means that the points make a continuous curve or surface. There we are. An ellipse is the locus of points whose distance from two fixed points add up to constant. So f and g both add up to a constant. So no matter where we are on the ellipse, we can add up the distance to point f and a point g, and it will always be the same result. Always add the same value. Okay, Foki. So that is the locus. That's what the locus means. Describe the set of all points P on a plane that are equidistant from a fixed point O. This basically creates a circle. Next question. Describe the set of all points P on a plane such that the distances from two fixed points F and G add up to a constant. So in this case it's ellipse. An ellipse with foci at F and G. Describe the set of all points P on a plane that are equidistant from two fixed points A and B, such that AP equals BP. AB equals BP. We can describe the set of all points P on a plane that are equidistant from two. So this seems to be an ellipse as well. Perpendicular bisector of A and B on a plane that are equidistant from 2 points A and B, such that AP equals BP. Set of all points P on a plane that are equidistant from two fixed points A and B, such that AP equals BP. Okay, so I get the point, I get the question. I didn't fully understand what the question was about. So describe a set of points P on a plane that are equidistant from two fixed points A and B. So you have P throughout in a way that it's the same distance A and B from fixed points. AP would equal BP. So the same distance. So in this case you have this perpendicular bisector of A and B. So it's a bit weird, but the point O is 5 centimeters from the line L. How many points are both 3 centimeters from the line L and 3 centimeters from point So you have the line L. It's 5 centimeters from the line. So the distance here is 5 centimeters. How many points are both 3 centimeters from the line and 3 centimeters from point O? So it's somewhere around here or here. So there's none. 2 points. What the hell? Points 3 centimeters from the line L lie on a line parallel to L. Yeah, so this is O. I get that. I get this is 3. One of which is the line M. Okay. The points 3 centimeters from the point O lie on a circle. It's like you have this A and B. Both would be 3 centimeters. Okay. The points P and Q are 6 centimeters apart. How many points are there that have the following conditions? Both are equidistant from P and Q. Both are 5 centimeters from P. 5 centimeters from P. So in this case, 5 centimeters from P. So P and Q, you have basically one would be here and one would be here. You have 2. So this is P and Q. One would be here and one would be here. So the points equidistant from P and Q will lie on a line L, perpendicular sector of P and Q. 5 centimeters and 5 centimeters is 2 points. Of all the points on the line L, only A and B are 5 centimeters from P. Yes. 3, 4, 5 triangles. Cool. The lines L and M are parallel and 10 centimeters apart. P is on line L, P is on this line, and Q is on this line. Okay. How many points are there that are equidistant from L and M, and also 13 centimeters from P? 13 centimeters from P. It could be L and M, so it could be this way, it could be. So that's the line. And how many points? Also 13 centimeters. And these are parallel and these are 10 centimeters. So you could go like somewhere around here, 1 and 2, L and M, and also 13 centimeters from P. Talking about P, so 2. Yep, so that's correct. So we have A and B. A line on the line N, yeah, which is also parallel and midway between L and M. Of all the points on the line M, only A and B are 13 centimeters apart. O is a point on line L. How many points are there that are both 5 centimeters from O and 3 centimeters from L? So it should be somewhere either here or here, so it's like 2. What? How many points are there that are both 5 centimeters from O? Okay, and 3 centimeters from L. So it could be somewhere around here. Oh, 5 centimeters from L. Yeah, so it could be here. 5 centimeters here, 5 centimeters here, 5 centimeters here, 5 centimeters here, 5 centimeters here. But keep in mind it's only 3 centimeters. Are 2 points 9 centimeters apart on the line now. How many points are there? How many points are there that are both 5 centimeters from O and 6 from Q? So it's 5 centimeters, but with the contingency that there's also 6 centimeters from, so it's somewhere around here. 5 and 6, somewhere around here, somewhere, so it's like 2. The point's 5 centimeters from a line, a circle, center O. Okay, radius 5. So the point's 6 centimeters from Q. Line. Okay, so the instructions for finding the treasure say it is buried 8 meters from the fence. 8 meters from the fence. It's buried 7 meters from the monument M. It's buried south of the monument and east of the fence. Eight meters from the fence. So 6 meters from the fence. This is the fence. 8 meters. Okay. So 8 meters. So it should probably be A or B. It's buried 7 meters from the monument. It's buried south of the monument and east of the fence. South of the monument. This is south. And this is east. South of the monument. Where is the treasure buried? It's buried 7 meters from the monument. Now, the monument, 7 meters. I'm guessing it's at B. Points 8 meters east to the south lie on the line M. L. Yeah. L. 8. 0.7 meters from the monument lie in a circle center M. (3D space). Fixed point O. Set of all points P in a 3D sphere. So we got 3 questions, 3 fault answers, false answers. That's that. So this is the deal with. So it's like the notion here is that you try to visualize the position of the. So you have a line and you have a circle. And then So let's we're through with the sets. Let's functions. Okay, so let's see what else do we have. So mapping, given two sets S and T, a mapping or function f from S to T is a rule which assigns a unique element y belongs to T to each element x belongs to S. So let's revise that again. So we have S and T, these are two sets. Okay, so a mapping or a function f from S to T. So we want to map from S to T. From S to T is a rule which assigns a unique element y belongs to T. Y belongs to T. Yt to each element x belongs to S. Assigns element y belongs to the. Oh yeah. So that's basically what mapping is. You have sets. You have elements in a given set S and T. So you have S and T, and you have say you have 1, 2, and 3 for S, and then you have I don't know. It could be 2, 4, and 6 for T. Mapping is about connecting each element in T to an element in S. So in this case, be it whatever relationship that is. So in this case, it's a double relationship. So 1 would be mapped to 2, and 2 would be mapped to 4, and 3 would be mapped to 6. And that's what this is all about. So let's read it again. Given two sets S and T, a mapping or a function f from S to T is a rule which assigns a unique element y belongs to T. In this case, these are set its elements here to each element in X belongs to each element in X belongs to S. Symbolically, we write this mapping as f, which is a function such that S is mapped to T, or it's a function for X where f is given the x. This use of the colon should not be confused with its usage meaning, says that. Oh, so in this case it doesn't mean such that. Set S is called the domain of f and t. Of f and t is called the range of f. Let's quickly, like really quickly revise uh, the locus here. And if you take a look with where was it again? The set of all points. That's not what we're looking for. So in the notations, where we had, where was it? Set notation builder. I think it was in here. As you can see here, so we have a domain of a function. So whatever it is, yeah. So the domain of a function, 1 over x is called f in this case, in this notation here. That's f of x. So it should be stated that the set S is called the domain of f, and T is called the range of f. Each point f of x belongs to T is called the image of x under f, or the value of f at x. Yeah, so that's and the collection of all such image points is called the image of f. In general, whenever a new mapping is given, we must check to see that it is, in fact, well defined. In other words, we must verify that x equals y implies fx equals fy, the function itself. That means we will use this requirement several times throughout the text. Okay, so I think it makes sense now. Now, to quickly or simply put this, so assuming you have two sets here, S and T, mapping is about connecting or assigning each element that belongs to T to elements that belong to S. And the mapping is generally denoted by this formula here, or this notation, for S is mapped to T, or a function where x is f of x. The S is called the domain of f, and T is called the range of f. Now let's quickly, like really fast. Now this is the domain. The domain is basically the function of x and the range. So you can see the range is fx, and x is the domain. So you would apply x to fx to get whatever result you desire. So the fx, this is the range of the function, and the domain, the elements of the function. So you see, assign the elements to the range to get the precise values. And in that sense, if we take a look here at what the book is saying, so the set, so in the definition, you basically assign x to fx. So you assign x, which is the domain, to the range, which is fxs. Remember, s is the x-axis and the t is the y-axis. So you assign the element to the function, and that's how the mapping is actually done. So the S is called the domain, and the range that you apply, the range or the results you get from applying the domain is called the range of t. Now each point fx should belong to t is called the image. Now every point you get as a result of applying the domain to the range is called an image. Okay? Image of x under f. For the value of f at x and the collection fx belongs to t where x belongs to s, of all such image points is called the image of f. In general, whenever a new mapping is given, we must check to see that it is in fact well defined. In other words, we must verify that x equals y, and the function of x equals the function of y. We'll use the requirements. Okay, we'll get to see more of that as we proceed. Now, A is a subset of S, is a proper subset of S. The set fx, where x belongs to A, is called the image. So the result is the image of A under f, and is denoted by f of A. If f is a mapping from S to T, and A is a subset of S, then the restriction of f to A, denoted by f for something fa, is the function from A to T, defined by, this is a bit weird, isn't it? X belongs to A is called the image of A under f, denoted by f. Is a mapping from S to T, and A is a proper subset of T, then the restriction of f to A, denoted by f, restriction or sometimes fa, is the function from A to T, defined by x belongs to A after fx belongs to T, its complement, then any element x belongs to S such that fx an inverse image. You should write this down to properly understand this. I'll have to do this on paper. I don't have the paper with me. I can't show you the paper because I don't have the drawing tool. But I'll try to draw this and explain it on briefly recap on it in the next video then. Thank you for watching, guys.